Okay. Okay, so good morning, everyone. We're continuing with chapter 4, actually. So last time we talked about um, mechanical energy, right? Like the different types of energy. We had kinetic energy, we had gravitational potential energy, and also elastic potential energy. So KE, and then U is potential, but we have two types of potential energy, which is gravitational and also elastic potential energy. So I'm going to label that as UE. So KE is the general equation for energy. Kinetic energy is 1 over 2 mv squared. This guy is potential energy. UG equals to mgh because this guy is related to gravitational force, right? This is why we have the mg there. And then for UE, it is related to our elastic force of the spring. So our equation is 1 over 2 kx squared, where k is the spring constant, x is your extension or compression. This is the energy. But when we are talking about work, we need a change in energy, change in E. So whatever energy that you have, there must be some change if we want to talk about work. So for example, change in KE. So there should be a KE final minus KE initial, and change in UG. So change in UG. So M does not change, G just does not change, H is the only thing that can change here. So mg delta H. Sama juga untuk KE. What can change here? Only the velocity. So you would have mv squared minus 1 over 2 mu squared. Mass does not change unless you are some kind of superhuman being. So your mass does not change, only the velocity changes. So that is how you get to know you have work, when the velocity changes. And when the height changes, you are lifting the ball or the ball is going down, the height changes, therefore you would have a change in potential energy. And also for elastic potential energy, when your spring is not doing anything, it's just like laying there, minding its own business, nothing is happening, there's no work done, but it has some potential energy. But when you extend it or when you compress it, compress bagi makin kecil, so it becomes smaller, and when you extend it, it will become, it will become bigger sebab kita extend. Okay, so dia jadi what do you call it? Dia jadi kecil, dia jadi stretch lah, dia jadi stretch. So we have the stretching and also the compressing. So stretching is positive delta X, compression is negative delta X. Sebab dia mengecil. Okay, so your changes is related to the position of the spring ataupun the compression or the stretching of the spring. Therefore, only X can change here. So when you're talking about delta UE is 1 over 2 KX final minus KX initial lah. Okay, susah pula nak tulis. Okay, so KX final minus, 1 over 2 KX final squared minus 1 over 2 KX initial squared. Your K does not change, it is the property of the spring. If your spring is hard or spring is soft, so K ni bagi tahu kita property of the spring. So benda tu tak berubah. Walaupun kita stretch ataupun kita compress, it's the same material, right? So the K does not change. So the only change here is X. So when you have a change in the X, you would have work done. Okay, so then I told you, when you have a change in your system, when you have a change in energy in your system, for example, you have, what was the example last time? We had a spring that was connected to a mass. And I told you if this guy extends, we are actually extending the spring, right? But this mass goes down by H when we extend it. So this is the new position and this is the new length of the spring. So you would have a decrease in potential energy, gravitational potential energy. You would have a decrease because why? Macam panjang sangat budak lah ni. Kita buang sekejap. Make this smaller. Okay. Okay, so sekarang ni situation kita adalah kita ada spring and then we have a mass. And then I extend the spring. I'm actually stretching the spring, but at the same time, I am lowering this mass. Now this mass and this spring is connected. Therefore, they are one system. Kalau diorang tak connected in any way, then they are separate system. But however, now they are connected together. So if the spring experiences changes, the mass also experiences changes in its position, right? So they are connected. Whatever change that happens to the other guy too. So they are within the same system. They are one system now. So now the spring is being stretched. Therefore, the mass goes down. So we can observe that we will have a change in UG. So our H decreases, right? Let's say I started at a height of 10. Now it is at a height of 7, let's say. So MGH is our equation. If there is a change in UG, it becomes MGH final minus MGH initial. And our M, let's say our mass of the object is 7 kilogram. So let's just put that 7 times 9.81, and our final is 7 meter. And then this guy is 7, 9.81, and this is our initial, so that it is a 10. So you will get a negative change in the potential, gravitational potential energy. So this negative change, where does it go? Where does it go? So you would have apa ni? Need to calculate. So 7 times 9.1 times 7 minus 10. So I would have minus 206.01. So this means that the system is losing energy. Remember, if we have negative work ataupun a negative change in energy, it means that we are losing energy from the system. But where does the energy go? Remember that energy cannot be created nor destroyed. It has to go somewhere. If I'm losing, I need to transfer it to someone. So this guy is losing energy, but this system is not being acted on anything else except for the mass. Did I say I stretched it? Let's say that it's only, okay. Sekejap saya tengah ingat balik apa yang saya cakap tadi. Tadi saya cakap saya stretch, tapi ada mass. Tapi kalau saya stretch, saya kena letak force. Okay, tadi saya cakap I was stretching the spring and we have a mass. Okay, abaikan yang saya stretch tu. If I was stretching this spring, I would have to apply a force, right? So sekarang ni our stretch is caused by this mass. Okay, so the force acting on the spring is the mass. Let's say spring kita macam ni, kan? Spring kita tak buat apa-apa, dia tengah duduk saja, and then tiba-tiba mass ni dilekatkan kepada spring. So this mass has some weight called mg. So this mg is force that is pulling the spring down. So this guy ada F applied onto the spring, which is mg, and this guy does not like that, akan berlaku pergelatan di sini. Fe pula dah, Fs. Okay, but this is not the point of this story. The point of this story is the force that is acting on the spring is actually by the mass, not by me. I said I was stretching it. No, it was the mass that was dragging the spring down. Okay, so now we're talking about the mass going down, right? From the initial position, it got extended to 7. Now we want to know, where does this energy go? I told you the system has to maintain the energy. If one guy loses, the other guy gets it. So let's see. So UE equals to 1/2 kx squared. This is our equation. but we want to know if we got any additional. Okay. So I told you this has to go somewhere. So I'm saying, okay, this guy will be transferred to the spring. So the spring punya change in UE will be, the spring punya change in UE will be positive 206.01. It will become positive. It will take this guy punya loss of energy and take it and make it as its own. And then 1 over 2 K. Tak cukup tempat lagi. Bila nak tulis pasal UE je tak cukup tempat. Sekejap. I'm gonna make this smaller. Kalau soalan boleh tanya, just interrupt me. Group. Okay. So hopefully we have space now. Okay, so now we're talking about UE, which is 1 over 2 kx squared. Okay, and I said when we're losing energy, it gets transferred. Okay, so this becomes change in UE. It has to gain something. So this gain will be equal to whatever that was lost. So 206.01. So now we say 1 over 2 kx squared final minus 1 over 2 kx squared initial. Whoops. So since it was extending, right, we would say that this extension was due to the increase in potential energy that we got from the loss here. So dan adalah value-value dia, I can't make up the values right now sebab dia kena sama so susah sikit lah saya nak buat value merepek kat sini. So whatever that is lost, it will be gained by something else. If this guy gets compressed, let's talk about when it gets compressed. Yang ni negatif, jadi ni jadi positif kan? Now let's talk about when it gets compressed. Saya kena apply force, susah sikit ni. Kalau nak compress, saya kena tolak dia. Which means I have to apply a force. I need to consider that. That is going to be difficult. Kejap. Let's see if we have other examples. So in an isolated system of objects interacting through conservative forces only, the total mechanical energy of the system remains constant. So this is what we saw just now. So the U initial plus Ki initial, but in this case, we just saw UE plus UG. Our K tak ada motion kan? So our K is equal to 0. Okay. Yang ni adalah U ni dia refer to both of the potential energy. Kat sini tulis satu U je, but it refers to both. So if you have both, then you just put in both. But in this case, we don't have kinetic energy. We only have the change in UE. So our UE, this is UE initial, UG initial, or UE final plus UG final plus 0. So just now we saw that our UG reduced by 201.6. And then this change was picked up by our UEF by 206.1. Wait. No. UE1. No, that was the final state, sorry. To UE final is the last state, so we got increased. This guy was decreased. So if this guy started with nothing, we started with not doing anything, right? We started with initial condition was not doing anything. There was no motion, nothing. And then when we put the mass, baru ada perubahan tu. So the initial state was actually equal to 0. So when we put the mass and it extended the spring, this guy got extended by 201. Sorry, this guy expanded its energy by 201. This guy lost, it is still equal to 0. So this is the conservation when we started with nothing, when the initial condition was not doing anything. Okay. So this was a little bit hard punya example sebab dia spring yang vertical. So selalunya kita punya example senang sikit. Sekejap, let's go for an easier example. Okay, so in general, a non-conservative may also be present, which is friction. So the ones that we have talked about is called conservative forces, elastic force, gravitational force, and also, what was it? Itu je lah kan. And then non-conservative is something that makes you lose energy from the system. It's called, in this case, we are just going to focus on friction. Another type of non-conservative force is air resistance, but we're not going to talk about that in our syllabus. They can complicate things. So if non-conservative forces are present, then some of the initial mechanical energy will be lost due to the work done to overcome the non-conservative force. So however, the total energy for the whole system is still conserved. Walaupun ada friction, and the friction makes it lose energy, this loss of energy will be compensated somewhere else. Sebab dia still kena maintain that total energy kena sama. Initial dengan final kena sama. So let's say situation kita tadi, we started with doing nothing, right? So I said, oh, this system ada friction sebab spring kita dia bergeser dengan dinding. Contohlah ada friction So this guy would be UE initial plus UG initial plus 0 for the KE, and for the friction, dah start lagi. So and then for the final state, kita akan cakap UE final plus UG final plus W and C. So semua ni dia kena equal to 0 juga. So adalah benda yang akan compensate untuk WNC ni. What is WNC? The work done by non-conservative force. So instead of 201 plus and minus 201, value dia akan berubah sebab dia dah kena kacau dengan benda Allah ni. Okay. So when we don't have non-conservative forces, it becomes easy. We know that, oh, this guy gains, this guy loses, or this guy loses, this guy gains, and the value would be equal. However, when we have non-conservative force, dia jadi complicated sikit, and kita punya value punya increase and decrease tu jadi berbeza. Okay, so we are going to look at that.
Betul.
Yep.
So maksudnya konservatif ni dia tambah ataupun tambah apa-apa pun dia akan equal to 0 juga. Walaupun ada non-conservative tu. Macam tu
Ayat yang sebelum ni ke awak tengok ni?
Yang ni.
Okay.
Dia akan tambah apa-apa pun dia akan equal to 0.
Dia tak semestinya equal to 0. Sometimes kita punya initial condition tu dah ada energy. Example yang saya bagi tu start from 0 sebab saya nak senangkan soalan dia. But sometimes our initial condition can be dah ada energy siap-siap dah. Contohnya contohnya saya ada incline and bola saya kat sini. This is my starting condition. And my starting condition ada height. So I can say that, oh, this guy has UG, saya selalu tukar, UG equals to MGH. This is the initial condition of this guy. What about its kinetic energy? So kinetic energy kat sini adalah equal to 0 sebab dia tak bergerak lagi, right? So this is my E initial. Okay, I think this is going to be an easier example to explain. Let's do that one. Chapter 4 part conservation of energy ni, saya rasa it's going to be challenging for students. So selalu student saya akan cakap dia rasa susah. So please just interrupt me if you need more explanation sebab memang topik ni dia macam confusing sikit. Okay, so we started with this ball on an incline. I want to know what is my initial energy for this system. The system is the ball. Okay, not the incline. The system is the ball. The ball is not actually attached to the incline. It's just rolling off the incline. Anggap incline ni jalan je lah. Okay. So the ball is the system. So the ball starts with a U that is equal to 0. Sorry. Starts with a velocity that is equal to 0. Nanti korang confuse pula. Velocity initial adalah 0. So I immediately know that my KE is equal to 0. Because why? Because it is 1 over 2 mv squared. And the mass does not change, only the V. So the V in this case is 0. So it's 1 over 2 m times 0. So it's 0. And okay. Sekejap, So this is our initial condition. So now our UG, I have KE and I want to know what is my UG. My incline is 10 meter from the ground. So I have mass, I have gravity, I have some height. So I can say, oh, this ball has some UG. So this is going to be, let's say the mass of the ball is 2 kilogram. Okay, so 2, 9.81 and 10. Okay, so now I say that, oh, my initial energy for this ball is equal to 0 plus 2 times 9.81 times 10. So let's say EI equals to EF. This is going to be our equation for conservation of energy. And my KE is equal to 0 and my UG is going to be equal to that. This is the initial, KE final plus UG final. Okay, KE is equal to 0. This guy is equal to 2 times 9.81 plus 10, 29.62. Okay, can anyone guess what will be equal to our final energy? What will be equal to our final energy? What is the value of our final energy? Come on guys, saya dah kasih hint kat situ dah. What is the final energy guys? Come on.
Doktor, bukan sepatutnya yang MGH tu darab ke semua?
Darab? Saya salah kira ke? Yep.
Dapat 196.
Oh, sorry.
And dua.
Thank you. Okay. Saya darab 2 je kan? 196.2. Okay. Betul lah korang confused. Okay, so what is the equal to the final energy? What is the value of final energy? Anyone? Equation ni cakap apa? This one, hint. What is the final energy, guys?
196.2.
Yes, it will be equal. So if I get 196.2 for my initial energy, I will get the same for my final. Cuma saya tak tahu je dia pergi mana, kat KE ke, kat UG ke. So this is what we're going to find out. So now my ball drops down the incline and dia laju lah kan, dia makin laju. And at this point it stops sebab ada penghadang. Saya letak penghadang kat situ. So dia stop. So now my V is equal to 0. My V is equal to some value. But now my height of this ball is on the ground. Therefore, it is 0. So now my KE is 1 over 2 mv squared, whatever that is, plus mg0. My favorite part is equal to 0. So I would know that 196.2 is equal to 1 over 2 mv squared. So I can actually calculate, hey, what is the velocity at the end of this incline? I can calculate. So it's equal to 196.2 equals to 1 over 2 times 2 v squared. This cancels out. So square root of this value will tell me that the velocity at the end of this incline is actually 14 meter per second. So this is how the energy works. This is if we have all the forces are conservative forces, tak ada friction. That is what it means. our EI is going to be equal to our EF, tak ada kacau benda lain. So this is our, the balance lah dua-dua. So the increase in UG, the energy from UE, tadi increase kat sini, the power from UG is transferred to KE. I wouldn't say transfer lah, it's converted into kinetic energy. And because it loses the kinetic and it loses the energy and it is transferred to kinetic energy. We started with 0, we gained. We started with something, we lost. So it has to be balanced. Okay, so everyone okay with this example?
Okay.
Itu susah sikit kan, nanti kita akan go back balik. Okay, so now let's talk about when we have friction. Okay, so now when we have friction, my EI is still going to be the same with EF. But now I have this guy. It's still going to be the same. Tapi UF dengan KF tu akan terganggu sikit lah. So UI plus KI minus non-conservative work done by friction. So if I put it in my initial condition punya side, this is the initial condition punya side kan. If I put it here, it will become a negative sign. If I put it on the other side, UI plus KI equals to UF plus KF, it will become positive W and C. Okay, kena ingat yang ni kalau dekat initial condition dia akan jadi negatif. Kalau nak transfer ke sebelah sana dia akan jadi positif. Dua-dua betul. Dua-dua akan bagi jawapan yang betul. Okay. Now let's use this equation. If we have friction macam mana? Okay. I'm going to use UI plus KI, UF plus KF. Okay. I want to discuss why it's a negative in the initial condition and why it's a positive in the final condition. Okay, so when we have this negative sign, let's say my initial yang kita tahu from our example just now. Saya nak lukis kat mana ni. Tu kat sini je lah. So, okay. So we know that we started with 196.2. So sekarang kita punya final condition ni akan berubah. So now kita start di sini, kita ada non-conservative work done. Kita akan just anggap it's a value. I would say it's 10 joules. Okay, this is the work done by our non-conservative force. Is equal to 10 joules. Mana datang? Datang daripada friction. Incline kita tak smooth. Okay, so I write down my KE is equal to 0 sebab kita start velocity 0, right? And my UG is 196.2. We started at a height which is 10, so I calculate that and it is equal to 196.2. Now, I haven't started my journey yet, so I don't have any friction yet sebab kita started with not doing anything yet. I know I told you there's a friction kalau static, tapi kita tak consider tu ya. So we're not doing anything yet, but I know that there will be loss of energy to friction. I know that there will be loss of energy to friction. So where does this loss go? So saya akan cakap, okay, if we started with this much of energy, this loss from friction, dia akan tolak macam ni. So what happens here? It will become 186.2. 1.186.2. So this is going to be equal to KE final plus UG final. And we know that our UG final is equal to 0 sebab apa? MGH. H kat sini kosong kan? Kita kat ground. So this energy is converted to kinetic energy. So let's see what happens to the kinetic energy. Previously, without friction, our final V was 14 meter per second. This was without friction. So can anyone guess what will happen to the velocity with friction? Apa yang jadi? Kalau ikut logik je. Kalau lagi kasar apa yang jadi? Lagi slow ke lagi laju ke?
Slow. Low.
Low.
No kan? Okay, let's see if that is going to happen. So our energy dia lost to friction, right? So dia dikurang sikit. Dan kekurangan ini, this final value is going to be equal to 186.2. So 186.2 is 1 over 2 mv squared final. So this is what we're left with, Ke final. Okay, ini Ke final. So we know that our mass is 2, so this cancels out. So square root of 186.2 gives me velocity of 13.65 meter per second. Was the energy conserved? Yes, the energy was conserved. Sebab apa? 186.2 is equal to 186.2. Hello. This guy, 186.2 is equal to 186.2. Dia still sama, initial dengan final. Cuma ada orang kacau so that initial tu jadi kurang. Ada orang kacau, nama dia non-conservative work done lah. So orang tu kacau and dia kurangkan initial energy. Dia kurangkan je. Dia kurangkan, so therefore we started with a lower initial energy and therefore our final energy will also be lower. Okay, so this is if I put the non-conservative work done on the initial side. Sebab kita lost energy. We know that we lost energy. So if I put it on the other side, okay, if I put it on the other side, so this would become 196.2 Ke final plus Ug final plus non-conservative work done, which in this case is positive 10 joules. Adakah sama? Sebab kita tahu yang ni KEF ni adalah 186.2 tadi kan? This is 0, this is 10. This is equal to 196.2. So kalau kita letak dekat final condition, kita tambah dia. But I think it makes more sense if you put it in the initial because you know that you're going to lose energy. So you start with a lower value. So it doesn't matter which one that you want to use. You want to use the minus on the initial or on the positive on the final, boleh. Dua-dua akan dapat jawapan yang sama. Mana-mana yang senang untuk korang. Okay, so we know that when we have non-conservative force, our initial energy will drop. Because kita akan start with a lower energy sebab kita lost some of it to friction. So we will start with a lower initial energy. Is everyone okay with that example?
Okay.
Yeah. Okay, nanti saya akan go back to spring nanti. I think it's a little bit confusing. Okay. Let's do this one. Yang ni, spring kita stop dulu. Yang ni memang susah gila example ni. Korang pening kali. Kita buat yang senang dulu. Okay. Okay, this one. So a crate of mass, 10 kilogram, is pulled up a rough incline with an initial speed of this guy. Okay, so let's put it over here. Let's write our equations. So we have our mass of 10 kilogram up a rough incline with an initial speed of 1.5 meter per second. So this is a rough incline. We know that we have friction. So friction is a yes. I would say friction adalah. Friction is present. Okay, a pulling force is 100 Newton parallel to the incline, which makes an angle of 20 degrees with the horizontal. So if I were to draw this, kenapa nak buat dash pula? It's a 20 degrees incline. 20 degrees incline and there is a pulling force yang suruh dia turun bawah. F pull. So FP is 100 Newton. Parallel to the incline. So our imaginary axis. This is going to be F pull. Now I can't differentiate this dash with F pull. Okay, so that is FP. So the coefficient of kinetic friction is 0.4 This is mu, friction is equal to mu R. So we need to know what is R to know what is friction. Friction is mu R. F is equal to 0.4 R. Okay, what else? And the crate is pulled 5 meters. So FP ni ditarik by 5 meter. So dari sini ke sini 5 meter. Okay, so now we're dealing with a parallel axis macam ni. Okay, how much work is done by the 100 Newton force? Okay, ni soalan ni senang. So what's the answer, guys? Work done is equal to, come on,
500.
apa?
500.
500. Where? How did you get it?
100 Newton multiplied by 5 meters.
Okay, so work done is force times S, right? If this guy is parallel to the S, FP is parallel to S, this is S. Therefore, kita tak payah nak kira apa-apa dah sebab dia parallel component. So, darab je terus. So, 100 times 5. Betul. So, it is a 500 joules. How much work is done by gravity? So, again, work is, we want to know what is the parallel force to the displacement. So, we have to do our free body diagram. Tak boleh escape. So, mg, this is mg cosine theta. This is going to be mg sine theta. So our work done by gravity will be mg sine theta darab dengan 5 because that is our displacement. So m is 10, g is 9.81, sine 20 degrees times 5. So that would become, I need more space. Can I make this smaller? Oops, small pula. Oh, kecil sangat kot. Okay je. Okay, so let's work this. I hope you guys can still see this. Okay, so kita ada apa tadi? Let me rearrange this one as well. Sekejap Whoop, jangan gerak, jangan gerak. And then our free body diagram somewhere else. Okay, over here. Oops, what did I do? So this is where our equations are going to be. Hello. Okay, so this is A. This was our A equation, A answer. This is B. So this is going to be 10 times 9.81 times sine 20 times 5. Okay, again, we are only dealing with the parallel force. Sorry, force punya parallel component to displacement. That is why kita darab mg sin theta terus. Okay, saya buat shortcut lah kiranya. Sebab kita dah tahu dah kan macam mana nak kira. Times 5. So I get 167.76 joules. So that is B. How much mechanical energy is lost due to friction? So we forgot about friction. And we forgot about our R. Free body diagram tak lengkap tadi. So we have R and we have friction. Can anyone guess what is our R here? Or should I write down the equations? Kita dah tahu dah, at this point kita dah patut boleh agak-agak lah. Is this box flying? No. Therefore,
Let Fy equals to 0. R is equals to mg cos theta.
betul. That our box is not flying, is on the incline. Kalau dia flying, lain cerita. So net Fy equals to 0. And what is in our, at y-axis, we have R minus mg cosine theta. This is going to be equal to 0. Therefore, R is going to be mg cosine theta. So now kita boleh kira kita punya friction. So friction is 0.4 times with 10 times with 9.81 cosine of 20. Therefore, friction is equal to, this is quite messy. Friction is equal to 0.4 times 10 times 9.81 times cosine 20. Kalau saya salah, tolong betulkan macam tadi. 36.87. Okay. Newton. So kita pakai the concept that we learned in chapter 3 to solve something that is in chapter 4. So this is why it gets a little bit complicated. Sebab kita kena relate balik. So friction is 36. We just want the parallel component. Is friction parallel to the displacement here? Is it parallel or not? Is it parallel? Friction and displacement? Yes, tapi dia
Yes.
terbalik. Therefore, our work done is work done sama direction positive, work done tak sama direction negative. So our friction that has an angle of 180 degrees with the displacement, which is 5, is going to be minus something. Ataupun if you don't want to put in the angle, boleh. You can just say friction terbalik dengan S, therefore it's a minus work. You just work with the values. Boleh juga. So friction is 36.87 times with 5. So that is, I need to write this down. 36.87 times with 5. And because they are opposite direction, I know that I need the negative sign. If I don't want to do this way, I can say 36.87 cosine 180 times 5. Boleh juga. Sama je, jawapan dia akan jadi negative 1. Negative 1 somewhere. This is negative 1. Okay, so that is 184.04. We are losing by this much. This is what we're losing. Okay, this is in joules. Next, what is the total work done on the crate? So the total work done on the crate, total. So we add all these things that we just calculated. We had force pulling. This is 500 joules. We had apa tadi nama dia? Gravitational force acting in the same direction as our displacement. That also contributes to the motion. Therefore, it also contributes to the work done. So this was 167.76. But friction, dia menghalang this motion to going down the incline. Dia menghalang. So dia sebenarnya opposing that motion and dia make the system lose energy. Sebab semua orang ni kena tarik juga walaupun ada friction kan. So they are actually doing extra work sebab friction ni. Friction ni jahat lah kiranya. So tambah semua, but we are going to lose from the friction. So 500 plus 167.76 minus 184.05. So 500 plus 167.76 minus, is right? Yeah, betul. 184.05. So hopefully my calculations are all correct. Tolong double check. This is the work done total. So what is the speed of the crate after we pulled 5 meters? So we started with U, which is 1.5. How do we know what is the V over here? How would we know? Kalau kita pakai approach initial energy equals to final energy, how would we do that? Okay. So kita boleh pakai balik yang mg, ke semua tu. Let's do that. So buang. Kita buat balik our example with the incline. So we started with this is not a ball, this is a crate. This is our crate. The U is 1.5. Therefore, korang jangan confuse ni meter per second. So this is going to give me KE of 1/2 times 10 times 1.5 squared. So this is 11.25. I hope I'm correct. Sekejap, let me calculate balik. M is 10 times 1.5 squared divided by 2. 11.
Betul.
Okay. So KE is 11.25. We know that this is 20 degrees. So this is 5 meter. Dia akan berhenti dekat sini. This is 5. Can I know what is the height that this guy traveled? Is it possible for me?
Boleh.
Boleh kan? Pakai Pythagoras, pakai apa nama dia, tangent or
Ish.
sorry. Pakai benda Allah tu lah kan? Okay, so you had 5 as your hypotenuse. 5
Sign.
is sin x. So opposite over hypotenuse, yes. So this is opposite. Okay, you want to know what is the opposite, right? So sine of 20 would be opposite over, opposite over 5. So sine 20 times 5 would give you 1.71. So if this box traveled by 5, it would have traveled down by 1.71 meter. So this is the decrease in height. So can you guys guess where we're going with this? Okay, so we are losing, what are we losing here? Kita punya mg, to start with, so let's do EI, cuba tempat. Okay, so EI is equal to E final, right? So EI is going to be KE initial plus UG initial equals to KE final minus UG final. But in this case, we don't know what is the height. So I need more space. Buang. Jangan buang bahaya. Let me duplicate this. Duplicate and then berbuang. Okay. Sekarang kau apa? Tak masa ke? Tak cukup masa. Sekejap. Sekejap korang. Give me a minute. Mg cosine theta. Kita nak buat equation kita. Sekejap, jangan panik. Okay, let's do it here. Okay. So kita tahu EI kita mesti final sama dengan EF. Tapi kita tak tahu height of our box, right? Because we just know that it's on an incline and 20 degrees. So let me write this down first. So kita ada friction. So this equation tak betul. Minus WNC equals to KE, berapa tadi? KE final plus UG final. Tak ada plus kat sini sebab kita ada minus kat sini dah. So saya dah letak dah the friction kat sini. So EI has to be equal to EF. But in this case, we have the non-conservative work done. Just now, we already calculate for the non-conservative work done by friction. And we found out that it is this value. So, mana saya tahu this is the value? Because this is the work done by friction. And the work done by non-conservative force is equal to the work done by friction. So, this is our value actually. So, 184.05. KE is 1 over 2. 10 and then our initial was 1.5 squared. UG tak tahu. UGI minus 18, sudah lupa dah. 184.05. Okay, and then kita nak tahu what is our KEF. Sebab kita nak tahu velocity dia at the end of the incline. I think that was the question, right? Speed of the crate after 5 meter. Okay. So we want to know what is our KE final because we want to know what is the final velocity, but we don't know what is our UGF and we don't know what is our UGI because we don't know what is the initial height and what is the final height. However, we know that the change in height is going to be minus 1.71. So boleh tak kita combine this equation? Kita akan cuba 1 over 2, let's just calculate that. So this is going to be 10 times 1.5 squared divided by 2. It's 11.25. So So this is 11.25. UG tak tahu. So this is going to be minus 184.05. Change in UG should be MGH final minus H initial. So this would be UG final minus UG initial. So UG final minus UG initial. So saya nak buat ke sini lah. So KE final tak tahu. And then change in UG, which is UG final minus UG initial. Okay, so saya buat macam ni. Benda ni dia bawa ke sini jadi negatif kan? So UG final minus UG initial. Okay, so I can know what is this guy because this is basically UG and I know what that is. So UG KE final plus with MG delta H. MG delta H. What is delta H? It's minus 1.71. So that is going to be, I don't know, M is 10. Hello, we don't have time. Cepatlah. Lagi 2 minit. Cepat, nak habiskan ni je. Okay. So this is going to be 10, 9.81 and this is minus 1.71. Kenapa minus? Sebab dia menurun. So kita ada decrease. Our initial should have a greater potential energy sebab dia dekat atas. Bila kita turun by 5 ataupun kita turun by 1.71 ni, we are losing our potential energy because we are decreasing in height. Turun. So negative kan? So change in UG should be negative. So 10 times 9.81 times minus 1.71, I will get minus 167.75. This guy is a minus. I bring this to the other side. So I will get 11.25 minus 184.05. Kat sini dia negatif kan? Kat sini dia jadi positif. 167.75. And this will be equal to KE. I need to write this somewhere. Saya panik. Sekejap. Let me finish this one. Lepas ni korang kelas apa? Whoopsie, jangan gerak.
Mana tak ada kelas.
Oh, okay. Tapi tak adalah saya nak ambil masa. Sekejap sikit je. Mesti korang macam bersalah nak bagi tahu saya nanti doktor nak extend kelas. Tak. Saya tak suka extend kelas. Saya paling tak suka kalau cikgu saya extend kelas. Okay, so next kita dah tahu kat sini. So kita akan ada orang suka kelas tambahan kan? Not me. Tapi saya buatlah kalau korang perlukan. But me as a student, I don't like it. So this will become KE final and kita tahu KE final punya equation apa? 1/2 M V final squared. So M is 10. This guy becomes 5, whatever. Kita buat dulu equation sebelah sini. 11.25 minus 1.184.05 plus 167.75 times 2 divided by 10. Alamak. Salah tu. 11.25 minus 184.05 plus 167.75. Saya rasa macam negatif lah. I made a mistake somewhere. Saya punya value semua betul ke? Itu tak yang salah. Okay, I need to double check on this. I think my values over here is wrong because it's not supposed to be negative. Because ada square root kat sini. It won't work if it's a negative. Kenapa yang 11.25 je? 1.5 divided by betul dah.
Doktor, rasanya yang 184.05 tu saya dapat 184.35.
Oh, ni 35.
Hmm.
Oh, tapi dia still lah 184 juga kan. Okay, tak apalah. I will continue this next class. But equation dia dah betul. Value dia mungkin salah kat sini. Okay, nanti kita akan discuss balik. If I made any errors here. Okay, so that is it for our class. So this is what you already saw in your lab as well. You had friction for your system, you lost energy, so you started with a lower value of energy. So itu akan affect your final as well. Okay, so that is it, guys. Take care and have a great rest of the day. Bye-bye.
Thank you, Doctor.
Thank you,
Doctor.
Thank you, Doctor.
Doctor,
Take
have a
care.
nice weekend.
Thank you,
And
Doctor.
if you want to submit, you have until
Doctor.
bye.
Thank you, Doctor.
Bye-bye.